Hi, everybody. My name is JD Williams, and I'm welcoming you to the screencast on applied optimization. The goal of this screencast and the subsequent ones that will come after this one will be to lay a solid foundation for applied optimization and how to use it in design activities. So a lot of problems will be solved here, and we'll look at a lot of problems. We'll solve it using MATLAB, essentially. Well, the text is Applied Optimization by Venkataraman, applied by optimization with MATLAB by Venkataraman. P. Okay. This is the text that we'll be using, and a lot of the questions in here will be solved here. So let's go in. First, before we go in, I'd like to discuss why we need to even optimize. Well, it stems from the concept of efficiency and effectiveness. Being effective is about doing the right things no matter the cost, right? If it costs, it could cost you your life, for example, but you get things done. I mean, it could cost you a lot of resources, but you get things done. But being effective, I mean, being efficient is way different. Being efficient is to use minimal resources and getting things done right. So I like the way InsightSquared.com explained it here. Being effective is about doing the right things, while being efficient is about doing things right. So you do things right with limited resources and get non-biased or an optimal, efficient result. Now, optimization is a tool that helps you drive efficiency, right? Uh, you can have certain constraints, right? And you're trying to find the optimal value of some design variables. So we need to understand that as we go forward. Optimization has become an integral part of design activities, and it transcends product design to service and strategy design. Now, the practice of optimization cuts across several disciplines, spanning engineering, science, fashion, theology, sports, and so on and so forth. You can have optimization applied quantitatively and qualitatively. This here I will explain as we go on. We have what we call multi-attribute decision making. You have a set of attributes and you're trying to find the best of them. So there are tools that are used, optimization tools that are used for that, which is beyond the scope of this screencast. But we'll look at it just for knowledge sake. Then you also have MODM, which is we'll also look at in subsequent sections, which is the multi-objective decision making, where you engage some kind of optimization tool also to solve that. Let me say that you need some kind of subject matter expertise to be able to to work out some optimization problems. For example, if I give you an optimization problem in mutual fund, for example, if you're not a business person or you're not business oriented, you might find it difficult. So you need to have some grounding, some understanding of uh, some areas before you can apply an optimizer. Just like talking to someone who is an artist and telling the person to optimize the deflection in the beam, right? That could be very difficult, right? But the person can employ an engineer, a subject matter expert to do that. So you need to have some kind of knowledge. So why I'm saying is that you might come across some problems that you don't have a background knowledge about. You have to read that uh, knowledge up somewhere and get a kind of grasp of what it is before you then start to solve the problem. Okay. Let's look at elements of problem formulation. One, design variables. This is very important. Design variables are unique or describe a particular design. I like the word here, particular, because it's unique to a particular design. For example, if I ask you to tell me the radius of a can that will maximize or minimize the cost of producing it. For example, well, I could give you another can that has the same geometry but different dimensions, right? The design variable here will be, let's say, radius and the height. And the design variables here will also be radius and the height, right? But they will be different across different design problems. Even though they have the same notation, they will be different across design problems. Okay. The governing rule here is that design variable must be linearly independent, right? That is very important. And the reason for this is, for example, you can have A1 as a design variable, B1 and C1. If C1 is in any way related to A1 arithmetically or through scaling, right? Maybe C1 is 2B1 and for example, then C1 is not linearly independent of A1, A1 and B1, right? This is very important because you could have X1, you can have A1, B1, C1, blah 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 blah, to maybe 100 design variables. What you would discover most times is that these design variables, some of them are not linearly, are not linearly dependent on one another. And if they're not linearly dependent on one another, it means that through scaling or some arithmetic operation, you can drive them down or reduce them down to workable numbers. So maybe you can drive them down from 100 to like 50 or to like 10 or to like 2, for example. So this is important to know. You don't want to say C1 here is a design variable because it's not. And if you put that in your algorithm or in your calculation, then you run into some problem. That's worthy of note. Also look at design function. This emphasizes the mathematical model describing the design problem, right? And it's split it into two, objective function and constraint function. The objective function and the constraint function. What are the objective function? Well, these are functions drives the search for optimal design variables. So in the case of the cylinder that we looked at early on, so we might say we'll look at an example. So I'm just conjecturing things here. Please don't stay on that. When we get to examples, that will solidify understanding, because those are practical things and you'll be able to get understanding. So I'm just giving an example here that, so maybe we're trying to minimize the costs, and the cost is related through these objective functions that says C is pi r squared h, for example. We're trying to minimize, we're trying to find the value of r that will minimize these guys. So now this expression here is the objective function, okay? Based on constraints, some constraints like the radius should not be should be between maybe 0.5 to 0.7, or the height should be between 1 to 7 meters. So all of those things, it means you can't go beyond these constraint values, or you can go below them, because if you do, then you'll be violating the optimization problem. This is worthy of note. It's important that we understand this, because it is these constraint functions that validates the objective function, right? Validates it. So let's look at feasible region of an unconstrained constrained function. So you have an unconstrained function. It means it's just it's the area enclosed by the constraint, right? For this is for constraint. Sorry about the mix up there. This is for constraint. For the unconstrained, there is no bound, right? It's open ended. There's no bound. Also, you also have the equality constraint. Okay, the equality constraint is represented by H, and the inequality constraint is represented by G. Just what do I mean by that? So you could have something like sorry about this going on here. So let me just stop that a little bit. Okay, allow you to run its course, and then so let me take you back here. Sorry, it's a little bit of technical itch there. Okay, come back here. Right. So you could have something like this. X1, sorry about that, x1 minus x2 equals 0. 3x1 plus 0.5 x2 less than equal to 0. Okay, so this is an equality sign here. So the constraint is symbolically represented by f of x1, x2. I mean, sorry, h, that's h right there. We can call this h1. You might have several of them, x1, x2, and then you have g1, x1, x2. Okay, these are functions. All right. So let's continue with elements of problem formulation. Yeah. What are the governing rules? Governing rules of inequality constraints. Okay, that is also important for us to know, because you could have practically a lot of these equations are a lot. You have several number of them. So you could have first, let's repeat the number n of design variable is in the problem must be greater than the number of equality constraints. What that means exactly is that you must have the number of variables. So you must have the number of variables x1 plus x2 plus x3, say less than equals to 0. Oh, sorry, now we're talking about equality constraints. So that's going to be equal to 0. Then you have x1 minus, let's say it's 3x2 plus 0.5 x3 also equals to, let's say, 3. Then we have 2x1 plus 3x2 plus 2x3 equals 1, for example. Now, can you tell me the number of variables we have here? N is x1, x2, x3. These are, so n equals 3 right here. But we have 1, 2, 3 equality functions. So the set of constraints must be linearly independent also. So what I'm saying here is that m here is 3. So n equals m here is not too good. You need to have n greater than m. This is important. So if I take this out right now, let's take this out for example. Take this out. Then I can say that n is greater than m. Okay, n is greater than m. This is important. The number of variables in the problem must be greater than the number of equality constraints. You can also test the set of equality constraints must be linearly independent. Okay, so the equation 2, equation 1 is not cannot be scaled or cannot be directly gotten from equation 2. So for example, if I have this two equation, x1 plus x2 equals 0 or equals then as a 2x1 plus 2x2 equals 0. So I know straight away that this equation is just 2 times this equation right here. So if this is 1 and this is 2, equation 1 equals equation 2 is 2 times equation 1. That is not linearly independent because you can scale equation 2 to get equation 1. Okay, that's important. Okay, inequality constraints. Let's look at the rules there. So when we talk about equality constraint, right, it doesn't give some kind it doesn't give some kind of flexibility when you're solving, because it just tells you, so you have this and it tells you, say, x equals 3 all across y. So you have all of these. There's no flexibility. So it's on the line. It's valid only on that line. But if I say less than, so for example, I have something like this and I'm considering this side of the expression of the equation, that is not feasible. It means all of this side is valid. All of this side is valid, which gives you more room for flexibility, right? Gives you more room for flexibility. So inequality constraint provides more flexibility in design selection because it gives you a region. It gives you a whole region to consider. Okay. Now let's look at side constraints. Side constraints. These constraints are required because they provide a domain or range for the design variables. So we're looking at, so essentially side constraints will give you a range or domain for design variable x1. Let's say this is 5, and x2 or y, say this is 3. So 0 to 3 on y and 0 to 5 on x is the domain for which your feasible region will be contained. If this is 3 dimension, maybe you have another thing here coming out of the screen, then you have a hypercube or you have a polyhedron describing the feasible region, and we'll look at that as we go on. Okay, so elements of problem formulation continued. We also have the design space. Like I mentioned earlier, the polyhedron or the hypercube describe the feasible region for which the optimization problem is true, for which you have like the word feasible region means where you have feasibility of your optimization problem. Well, the Euclidean or Cartesian n dimension space generated by n independent variable and n plus 1 dependent variable. If I have y equals x1 plus x2, right? Y here is like we all know, depends on these two independent variables. So if I were to plot this guy like so, I have n independent variables. X1 and x2. In this case, there are 2, so it's my x1 and this is my x2. My y depends on them, so my y must of a necessity be the n plus 1 dependent variable. So it comes out at me on the screen so that you can have something like a surface, like so, like so, where this will represent some kind of level, height, h1, h2, or h0, h1, h2, so which means it can either increase upward or decrease downwards. Just for analogy's sake, but that's the whole concept, and that's what that's what it actually means. So an hypercube is formed when side constraints are employed, including a feasible region from which the optimal solution is chosen. We'll just explain that. And we'll stop here soon. Before we start looking at examples, I wanted to see the standard format here. This is the standard format for for on an optimization problem. You have something that you want to minimize or maximize, subject to some constraints, and these are equality constraint here. You can see them: h1, h2, h3 is subject to more constraint, g1, g2, g3. These are inequality constraint, and they are non-negative numbers. Sorry, did I just say non-negative numbers? Yeah. So in real life, they should be in some most of the questions, right? They are usually greater than 0. I mean, those variables x1, x2, x3 will be greater. And I will explain what this means later, because you don't have resources. You cannot have 0 resources. You can have negative resources. You can have negative time, for example. But we'll look at that to solidify examples. So another way of writing this is you have some lower bound I, xi, and upper bound, and and so on and so forth. Okay, so we will stop here today. We'll end here, and the next time we will look at some examples of how to apply everything we've learned so far. Thank you so much, and I hope you enjoy this screencast. If you like it, if you want to, you can subscribe. If you don't feel like, that's fine, but just make sure that you follow through the whole process to gain a deep understanding of what we're talking about. Thank you once again, and see you. Bye.